Okay, then let's start. So, welcome everyone to our webinar. My name is Hrvoje, and today I will be talking about Yocto. Uh, just a second. Somehow I didn't turn off my notifications here. Hopefully now it should be fine. Okay, so these are the topics I picked for today. First, I'll give a little introduction to Yocto project and what components it contains. Then we'll go into the BitBake, and then we'll cover Open Embedded Core and how, in combination with BitBake, it can be used to build Linux systems. And in the end, there will be a short conclusion. So. Why would you want to use something like Yocto project? Basically, the main reason is that building Linux distribution is quite complex, and that is especially true if you are building it for custom-made hardware, because then you have to do a lot of different configurations specific to that hardware. Now, if you really want to experience how complex is building Linux distribution, I would recommend you to check out this Linux from scratch tutorial, and it will give you a good guide how to build this distribution step by step, doing it manually without much of the tooling that Yocto provides. What else Yocto gives us? It gives us modular builds with reusable components. So it's relatively easily to switch targeting platform without having to change the whole build. And it's easy to build on top existing images and add your own functionalities. Now, what does Yocto project actually contain? So it is a set of tools, templates, and metadata that help us create these Linux-based systems. And out of all these tools and templates and metadata, I would say the two main components are the Open Embedded Build System and the POKey. Now, what POKey is, it's just a reference, or how should I say it, example Linux distribution that is built by using this Open Embedded Build System. And Open Embedded Build System is actually a specific project that is actually contained with the Open Embedded project and the Yocto project. So it contains two components. One is the BitBake. It's the actual program that is running the build. It's actually just doing what it's doing. It's processing these recipes. And the other things is Open Embedded Core, which is base set of this metadata and recipes that you can use to build all kind of packages and Linux kernels and configurations and stuff like that. So how this looks like in the picture is this. So we have a Yocto project with its tools and components, and one of these components is actually POKey, reference distribution, which is built on top of Open Embedded Core metadata, and it's built using this BitBake build engine. And of course, POKey itself adds two more layers. We'll discuss about this later on. One is called Meta POKey and other Meta Yocto BSP. And yeah, as I mentioned, these two things are actually contained together with the Open Embedded project. So let's now jump directly to the BitBake. What is BitBake? BitBake is actually configurable generic task execution engine. What this means is it's not specifically made for building Linux images. It can be made to build any kind of application. For example, in theory, you could use it to build your, let's say, C++ application instead of using CMake or auto tools, or maybe even using build Java application instead of using like Maven. However, as far as I know, it's only used in Yocto project for building Linux distributions. Now, what are these tasks that BigBake is executing? The tasks are actually just simple functions that contain either executable shell code or Python code, and they are mostly defined in the recipe files. Alongside the tasks in recipe files, we can also find a lot of variables that enable us to configure BigBake and the tasks that BigBake is running. So these tasks can be a bit more generic, and you don't really have to change them, and you can reuse them. So they'll run stuff based on the variables. The variables are not just defined in the recipes, they're also defined in all kinds of configuration files. And then how the BigBake actually works? Well, first it will parse all configuration and recipe files it can get its hands on. And based on these files, it will create dependency tree between the tasks, and then it will, based on the dependencies, execute the tasks in order. Now, what are the recipes? Recipes in principle are just text files containing code and variables. So usually one recipe is just a list of variables and tasks that is needed to build a single component of the whole system that we are trying to build with the BigBake. And usually each recipe defines 4 things. So first is some kind of a description and a revision of the component it is building. The second is kind of location of the source code and the other resources that are required for building the component. The third thing is the build instructions for building the component, and the final step is kind of an installation step. Now, however, since these notifications will not stop, just give me a second.
If it's of help, we didn't see your notifications.
Okay, good.
So they're only bothering you.
Important, but they're interrupting me with the sound and everything.
Awesome.
Okay, so sorry about that. Where did I stop? Okay, but recipes don't really need to follow these steps. They can be all kinds of different types of recipes, but usually they do. They follow this kind of 4 steps. As I said, there are just textual files that are stored in with the BB extension. And here is an example of very simple recipe. It doesn't do anything except that there is just one task that prints to the shell running do build. So basically, first we have this variable description with value first component. Then we have another variable product revision with value R1. And then we have this task do build that will be executed when the BigBake runs this recipe. So other than recipes themselves, we also have recipe classes. Recipe classes are used to reuse the tasks as much as possible and some configuration values. So for example, if we have like some component, actually multiple components that are built in the same way, then probably the best way would be to create a class, and then for each recipe of these components would then inherit this class. And here is the simple example of one class and one recipe that inherits it. So we have one task defined here in the class. So it's called doConfig. The usual convention is to prefix these tasks with the name of the class, because in case you are inheriting multiple classes, the conflict could happen if the tasks have the same name. Other than that, we can see here a command add task, which adds the task do config, and we also have export functions do config, which exports this function so that recipes can actually exit it and use it. Then we also have the recipe. Now it's called second component with revision R1, and we can see here it's inheriting my class. Then it has its own do patch task, which is added to be executed before do build and after do config task. Now, as you may notice in the first task that I showed, we had this do build task, which was never actually added to the list of tasks, like here add tasks. That is because we have one special class that BBake uses. It's called base class, and it's required by BBake. So it needs to be located in one of the layers in the classes folder. And why is this class special? Because every recipe that we have inherits this class implicitly and by default. So basically, we don't need to explicitly set inherit base class. It's the BitBake will implicitly inherit it by default. For example, that's why we have like this do build task available. Actually, I have one extra this do config here, which is not defined, but that's my error. So it should be just do patch before do build. But let's say the do config is also defined in the base class. Okay, then we also have recipe appends. So this is a mechanism to update the recipe without changing the recipe itself. And we'll see later an example why we would want to do this. But for now, how it works is that we have a recipe called first.bb with its own do build task and description and variables, and then we have somewhere else defined file first.bb append with a new task called do patch, and this task is added to be executed before do build. And now when we actually ask BitBake to build us this recipe first, it will take in consideration all the first.bb appends, and then it will try to build like one, like let's say sum of all bb appends and the original recipes. Okay, so then we also have layers. What are layers? Layers are just collections of related recipes, and by convention they are stored in the folders named meta minus layer name. Why are these layers special? Because they have their own config, which is located in the layer directory config/layer config. And what is usually done in this layer configs is actually you add this append this bb files variable, which contains a list of paths to all the recipes. So usually what you do is add all the recipes to this, all the recipes of that layer to this list. Then we also append bb path variable, which contains paths where BitBake should look for different configs and classes. And usually we just add the top layer directory to the bb path variable. Now I mentioned previously configuration files, and there are many configuration files that BigBake can have, but there are actually two mandatory configuration files that BigBake will fail to. It will throw an error if you miss them in your project. First one is bblayers.conf. This one specifies actually which layers BigBake can use in the build process and location of those layers. And this is the first file that BigBake actually parses. So first thing, when you run the BigBake command, it will try to find this bblayers.conf file and try to look for all the layers that are defined here. Other than that, we have BigBake config, which is also required, and this one actually contains a lot of variables that are actually just general BigBake configuration. We'll take a look at them in demo. But for now, let's take a look how some minimal configuration, BigBake configuration would look like. So it's not really required for like these folders directories to be called like build and meta example, but this is the usual convention. And we would run the BigBake from the build directory. So what the BigBake would do, it would look for config bblayers config, and in there it would try see which layers are defined. In this case, it should be one layer, meta example, and then in meta example, it will look for layer config. It would also look for BigBake conf and base class. Okay, so now we can do a short demo. I have prepared a project that is very similar to this minimal config, but I have also added a few recipes, so we don't waste too much time. Now let's take a look at it. So this is the root of the project. I have also downloaded the BigBake, whole installation of BigBake here. The things here are not that important, other than the executable is here. It's called BigBake. You should add it to your pod if you plan to use it from somewhere else and you don't want to refer it directly to whole pod. Other than that, there are also some other tools that are useful. For example, you have BigBake layers that it's a small tool that enables you to quickly add layers without having to like edit the all bblayers files, and it will, I think, even create the folders and layer config automatically. But in any case, this is not really important right now. Now let's take a look at our project here. So I have two layers now, meta example and meta example 2. I have my configuration, bblayers configuration in bblayers conf. For now, I have just included meta example layer. I have initialized here bb files variable to nothing, and which will be later appended in the layer configurations. And the bb files, for now, I have appended this top directory here, which is actually this build directory in the bb path. Okay, so we can take a look here at the meta example layer. We have a base class here which defines one task do build, which doesn't do anything except it will run do base do build, print running base do build. It will also print out value of the description variable, which will be useful later, and it also exports this to build tasks to be used with other recipes. We also have layer config. As I said, nothing interesting here. We add append to the bb path variable, and we also append to the bb files variable. Here we are using the glob syntax. So basically, our recipes can be found anywhere in folder recipes minus whatever slash whatever, and then whatever the name of the recipe. So basically anything that is in recipes minus folder. And in that folder, we have only one recipes minus folder, which is recipes example, and we have only one recipe here, which is called first.bb. Nothing special. We have description. Actually, we have two descriptions here. I will talk about this a bit later, but let's say for now, this one is the default one, and this one is, let's say, conditional, which will be applied in something case. We have also revision and one task do unpack that will be executed before do build. So now we've gone through this meta example, and it's the only layer that we have currently in BitBake. So if we run BitBake first, it should now execute this recipe if everything is configured correctly. On secondary, you saw that BitBake was executing task 1 of 2 or 2, but it was very quick. So and you can also see the summary here that it entered 2 tasks, which 0 didn't need to be run. Basically, what BitBake has is this cache, and it's always checking if some tasks were already executed and don't need to be rebuilt. So if I would like rerun it now again, we would get this attempted 2 tasks, of which 2 didn't need to rerun. So it's kind of smart. So you don't need to do full builds always. It will remember what it has built previously, and it will reuse it for future builds if possible. Okay, now we can check what really BitBake created. So we have this cache directory, which is currently not really important for us, and there's also this cache. What's really important is the work directory, which usually contains the output of the build. Now we have one recipe here, so it contains only one recipe, but usually it would contain first the image recipe, and then under it there will be like subdirectories, which are sometimes very confusing to find actually where your output actually is. But now it's very simple, and we can see in this temporary directory we have some logs and some run files. So if we open one of them, so each task that was executed actually generates its own logs and runs. So if we open this run, this shows you how actually the task looks like when it was executed. So there's a lot of bloat that BitBake actually adds to your task here. But as you can see now, do build, here is our code from the do build from the base class. Also, we can open the log, and we can also see that the printed description was the first recipe. So if we go back to this, we can see, yeah, it printed this correct description, first recipe, but it didn't print this first recipe something. Okay, now we can go into the second example. So this is another layer where I added a BB-append file that is supposed to append another task to the first recipe, and it should be executed before this do unpack. So if I include this, I should see somewhere in the output directory that the do fetch was also executed. Moreover, I have also added this myConfig variable with value something. Now, how would I use this value? If we go to the bitbake configuration, I haven't really much talked about these files because I mean it contains a lot of variables, and later on we'll see in Yocto it has them even more and a lot of configurations. So most of them are not. It's hard to say not important, but for now they are not that interesting for us. For example, some directories that bitbake actually uses, so it's not really currently that important. But what is interesting here is that you can include other configuration files. Here, for example, I included this my config from the other layer. Why can I do that? Because exactly because of this bb path variable. So I have added this layers directory to the bb path, so the bitbake actually knows where to search for the configs. So I don't really need to specify the whole path to the other layer. I can just say conf my conf, and it will look through all layers and try to find this configuration. Okay, and there is one special variable here that I would like to emphasize. It's this overrides. What this variable does, it allows you like kind of to override the values of certain variables, and I even think tasks. So it's a list of some values, and and then these values can be prefixed to any variable, and in case the value is defined in the list, the bitbake will use that variable's value. So I mean, this sounds a bit confusing, but let's go back to this first recipe. So if we have here description something, which is prefixed with something. So what bitbake will do, it will try to find the value of something in the overrides, and if it doesn't find it, it will use the default value. So then this is my the first recipe. And as you saw when we executed this task previously, it printed out first recipe. So it didn't print out first recipe something because something was not defined here in the overrides. Now, if you just do like something like this, it will print out. It should print out this first recipe something instead of first recipe. However, this is not really something that is that useful, like editing this overrides variable. I mean, you can do it, but the purpose of this is more like to have different kinds of configurations. So as you can see, this variable actually contains values of other variables like machine, target OS, and target architecture. And now I have added also the value of my variable value, which I defined previously, if you remember, in my config. So in completely different layer, I'm actually controlling the value of these two of this variable, and that's very useful. I mean, you can basically like this. You can basically configure the behavior of certain recipes without editing those recipes, and even without appending those recipes. If you know like how this recipe behaves, you can like and if it has some special prefixes, you can actually make it do something different. And now in this case, I will show you how it works. Let's go to the config. Now let's include this bb layers. Let's include the second layer. Hopefully this should be enough. I first need to remove the temporary directory because I don't have a good clean task here. So okay, and now if I run the big first, as you see, now there are 3 tasks executed. The third one is this to fetch from the BB append. And if we check out the logs for do build, you can see now it printed first recipe something because we have our my configuration here with this my variable set to something. So yeah, there are many things I could talk about regarding BigBake, but this was kind of a short introduction. I mean, as you saw, there are many kinds of assign operators. I don't really want to go into details now, but I recommend you check out the documentation for all the details. Okay, now that we know a little bit about BigBake, we can try to see how Open Embedded Core actually builds upon the
Do you want to maybe take a minute and answer?
Yes, sorry, I forgot
I was just
about the
thinking.
questions.
There is one. Can you see it, or do you want me to read it to you?
Yeah, I can see it now. Okay, does the double asterisk can be? Yes, I think so. I think this it supports. I mean, the standard glob syntaxes. So I'm not sure. It should support standard glob syntax, but I think it should be possible to use double asterisk also. And were there any other questions? No, I don't think so.
Not for
Okay.
the time being.
Okay, then let's continue to the Open Embedded Core. What is Open Embedded Core? It's actually a BitBake meta layer that provides us with foundational recipes and configuration that we need to build our Linux distribution. For example, it contains Linux kernel recipe that, of course, can be configured with different variables, and it can be also appended, as I showed you just now. A lot of basic utilities recipes. For example, you can choose between GNU Core Utils or BusyBox, or we also have init system recipes. You can again choose between sysv init and sysd. Bootloader recipes. Now you can, alongside with your image, you can build your bootloader, and you can also configure it. You also have choice between different C standard libraries that you want, or package managers, and a lot of other recipes. But it also contains base BB class that we explained before, and it also contains BitBake config. So the 2 files that were required by BitBake. And how do they look like? Well, they are huge files with a lot of, tasks and configuration, but in short, base BB class has these tasks defined. So we have this fetch, unpack, configure, compile, install, build, clean all. And they all have some default implementation, which we will check out later. But it also includes a lot of other classes that have their own tasks. So listing all of them wouldn't make much sense here, but we'll check some of them later. And of course, if you need to, you can also Google them and check them out yourself. And then we have BitBake config. Of course, a lot of variables are set there, and it also includes other configs that can be found in that are supposed to be found in other layers. In our case here, I would say the most interesting one is as our config, this local config, machine config, and distro config. Now, I don't want to say that others are not important, but I will not be explaining them now here. So you can kind of Google them and search them to see what the other ones do. So when we have all these files and all these recipes, now we can start building our image. And what we actually need to do, I mean, you saw previously that there are all kinds of different recipes. For example, you can systemd, you can use either systemd or sysv init. So what you need to do is select the packages, or how shall I say it, recipes that we want to use in our system. There are two options how to do it. You can try to create your custom recipe for building the image. I mean, it can be done, but then you'll have a lot of manual work, and it will lose the point of using the Yocto. But what the other things you can do is just use one of the image recipes that is provided by Open Embedded Core. And here are some of the images. There are at least 10 of them or something, but here are the basic ones that are usually used and built upon. So first we have this core image minimal, which provides you with a very small image that only has console base. Then you have this image core image base that's very similar, but it provides a full support for the target device. So everything that you define that your device has, this image should support it. And also core image full, that's also again another step more. So we have a full feature Linux system functionality. Whatever that means. So what is here important is that each of these images defines this image install variable, which actually has a list of all packages that are included in image. And if we want to take one of these images and we want to extend it with our own package or some of the existing packages that are not included in the image, we just need to do this image install append and just add, for example, I have added nano editor here. And you can do this in your own layer. So this append actually works the same way as appending the recipe works. So before we actually build the image, we have to select two big things that will actually give us, let's say, a flavor of the Linux that we want, flavor of the image that we want. And these are the distro, which defines the distribution, and machine, which actually defines the hardware that we are running on. So what is distro? Now, distro defines kind of let's say, overall configuration of Linux system. So for example, some of the distro level features are will our image support IPv6? Will it use systemd or systemv? Will it use, for example, X11 or maybe Wayland as a windowing manager? So this is what is actually selected with distribution. And how do we select distribution? Well, we just set the distro variable in our local conf file. If you remember previously, this local conf file will be included in bitbake-conf. Now, after we included it after bitbake-conf actually includes it, it will know about distro variable, and it will know which distribution configuration it should include. And this distro configuration should be located somewhere in the BB path. It's usually located in special layer that is called like the distribution layer. What's important for distro configuration? I mean, there are a lot of variables and configuration in distro configuration, but the most important one is this distro features that actually contains a list that looks like something like this, like IPv6, systemd, X11. There's also an option to remove some things from the distro, but I won't be talking about that now. Then we also have to choose machine. Machine similar like distro, but now we are defining the hardware specific features of the Linux system we are building. So for example, if our hardware supports real-time clock, we would add our RTC feature. If our hardware supports Bluetooth, we would add Bluetooth feature, similar like, for example, if you have some kind of USB or something like that. Again, setting a machine is done same way we set the distro, except the different variable in question. So now we have machine variable, it's still located in local conf, and then bitbake conf will include this machine configuration. Usually these machine configurations are located in special layers that we call board support package layer. Now these layers are actually just what the name suggests. So they add configuration and recipes needed to support Linux for specific hardware. And usually they don't just contain one machine, usually they contain, let's say, like a family of machines. And here we also have machine features, so a variable that, again, it lists the features that this machine should support. And now we can go to the demo. Just give me a second. I had some issues previously. Okay. Hopefully it will not crash. Okay, so I was first thinking to build my own project and everything, but it was a bit more complex than I expected. So I decided to reuse the Pokey reference distribution. So this is how the base Pokey directory looks like. We have bitbake here installed, and we have a lot of these readmes and documentation, but we also have three meta layers, which are important for us. This one meta, named just meta, this is the open embedded meta layer. We also have meta Pokey. This is meta layer that contains Pokey distribution. As you can see, config distro Pokey. And if we take a look at here, we have a variable called distro features, which defines a bunch of features that this distribution should contain. Okay, we can also see there are multiple distributions here in the meta Pokey distribution layer, and we also have a PSP layer, which of course should contain several machines. We have here support for BeagleBone, some edge router, and some generic x86 configurations. Okay, what's also very important is this OE init build environment script. This script also comes with open embedded build system, and it's very useful because when you run it, it will initialize your build directory, and it will also add bitbake directly to your path variable, so you can run it from whenever you want. Now, I'm not sure if I run it before this, so I will rerun it again. Source, oops, no, where are we? Okay, now we can source it. And usually if you don't have the build directory, I have created it previously with the same script. Here you would get something like script would warn you that it has created build directory with default configuration and stuff like that, but now there's no warning here. However, the script immediately recommends us that we can run bitbake on one of the common targets, and if you remember, you can probably recognize now these are actually images, and we can try to run this core image minimal, but I would leave that for later because I had some crashes today, so we don't want to do that now. But let's take a look at these meta layers in detail. So let's go into the open embedded meta layer. Now we have a lot of recipes here, as you can see, that are split into different categories. For example, if we dig a bit deeper here, you could probably somewhere find recipe for Linux kernel somewhere with a source here, and however, these recipes are usually not very simple. They usually include and require a lot of configuration, so it's not very simple to explain them in a few minutes. But if you are interested, if you're interested now, you know where to find them. What we can take a look at is, for example, base BB class and how it looks like. Again, it's a huge class, but for example, we can take a look at fetch class. Okay. Here is the fetch task. If I remember correctly, it's the third task. So it's a very simple task. It will get value stored in the source URI variable, and then if nothing exists, it will return. But if something exists, it will use this bitbake fetch class to download all the sources and source code and resource it needs. And then we also have unpack, which basically does the same thing, except it will unpack this from, I think, download directory to the working directory, currently set working directory. And of course, there are a lot more tasks defined here, and I think somewhere at the top you can see it inherits a bunch of more classes. What we can also take a look at now is bitbake config. Now again, huge file, lot of variables, lot of configurations, but we can take a look at all overrides of what's let's see. Okay, I think we are somewhere close here. Machine overrides. Okay, so here is the overrides variable that I mentioned previously when we were working with bitbake. As you can see, it contains again huge list of other variables based on what we can configure different other variables with. So we can use all these values as a prefix to our variables, and the two important ones I would say is machine overrides and distro overrides. So basically, we have this distro and machine distro values of distro and machine here in the overrides variable. So we can again, let's say, create variable and say pokey equals, I don't know, pokey. Then this value will be only applied for the pokey distro. And also now we can see here where it actually includes all these configs and distro configs, local configs, and stuff like that. Okay, don't say this. Okay, so this is the big layer config of the Pokey project. Again, I said there are three main layers that are we using here. It's meta, which is open embedded layer. We have distribution layer for Pokey, and we have this for different machines. And I also tried to add an example here. One more layer, which I added like hello world C. So this is how, for example, it would look like to include your own application into the image. So you would just add another layer. You would add, for example, recipe for that. Here I have built like a simple systemd service called hello world service, and which only runs this hello world C, which is defined here. So it's not Git repo or anything. It's just a local C file which just prints hello world. And here is the usual systemd service definition, which, as you can see, it contains just description and which binary should be executed to start the service. Again, for do compile task, I just called like a compiler to compile the C into the binary. And for the do install task, I moved this binary to the rootfs of the image, and so it's included in the image. Except for that, I think I also had to add here image install append, as I said. So this will append this hello world feature into the image. I probably forgot to mention in this local config. I mean, I mentioned it previously, but we have defined a machine here. It's emulated machine KMU x86-64, and we have also selected Pokey distribution.
Sorry
yeah.
to interrupt you. I just wanted to let you know that we have around 5 more minutes and another question waiting for you.
Yeah, I was just about to stop here. I was planning maybe to run a build, but maybe it's better to skip that for now. But okay, maybe if I just comment this, it could work without questioning everything. So if you would like to build an image now, you should be able to do just bake core image, and hopefully we'll see. Okay, so it started the building. You can see when you start the building image, you get a lot of information. So which distro you choose, which machine, and stuff like that. And while this is running, it shouldn't run too long, because I already okay. So I already did rerun previously, so it didn't need to rerun it. But in theory, now we could start KMU and start KMU and see work with our image as we wished. And if we included this hello world, it should be included in the. You could like see it in systemd logs, and you could check the status of the service. But I think that will be all for now, because I still have one more slide and we want to answer a few questions. So what is the conclusion? Basically, conclusion is that building Linux is very complex thing, and Yocto will not make it that much simpler, but it will provide you a lot of examples and references and already written recipes that you can reuse and pretty much simply just include in your image. And it's very modular, so you can easily extend those images with your own recipes, your own applications. You can very easily change configurations of images in your own layers, so you don't really need to go into existing layers. You just create your own layer, append some recipe that you want to change, and the bitbake will recognize it, and it will build it as you wish. And there are a few steps that I want to mention. Next steps that you could do. So first one is go to the Linux from scratch. This will teach you a lot about Linux and how it's built, and a lot about these features that I just briefly mentioned here. Then you can learn a bitbake, this specific language that bitbake uses in detail. It's not too hard. It's very simple, similar to the shell, kind of a combination of a shell language and Python. And then you can try to create your own distribution or PSP layer. And yeah, that's pretty much it I had to say. And now I'll try to answer the questions you have. I see the packages are fetched and built from sources. When we create our own recipes, is it possible to define a range of supported dependencies? As far as I know, I don't think so. As far as I know, maybe there is a feature for that, but I've never used it, so I can't tell you for sure. As far as I know, you define dependencies directly on the exact version. So, but yeah, now that you mention it, a lot of build tools today support things like that. So it's possible that Yocto has some kind of support for that too also. Okay, are there any more questions? I don't think so.
I can't see any. So I am thinking that maybe there are no more questions. But in case they are, maybe we will meet again for a sequel, a part two, a completion of what you presented today, Hrvoje.
Yeah, we'll see. I mean, this was very, very quick introduction in Yocto, and I didn't mention like maybe 20% of the Yocto stuff you need to know. I would probably need to organize a whole course on Yocto. But yeah, maybe we'll have a few more webinars on this topic. So if you're interested, we'll see what can be done.
Yep. It's actually not a bad idea to do maybe an entire course, but we will talk about it and get back to people.
Yeah.
In the meantime, thank you everybody for joining, and thank you, Hrvoje, for taking the time to teach us something today.
No problem. Thank you.
And I guess we'll see each other next time.
Yeah. Okay then.
Have a great
See
evening,
you.
everybody.
Have a
Bye.
great evening. Bye.